not even on there. Maybe it. Hi guys, welcome to Emily's YouTube channel. Today we're gonna review biology. Thank you for watching. Make sure you like and subscribe. Okay. So we'll start with Unit 1, if I could type. So Unit 1, which is going to be all about biochem. So that's going to be like atoms, what's all in their water, and macromolecules. So our big ones. Okay. And so we'll start. So our biggest thing that we've got to talk about. Good morning. Biggest thing we've got to talk about is what an atom even is. So just to review that for the very, 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 very basics. So if I were to draw this atom, let's say this is my nucleus, and let's say this is going to be my orbitals. I've got two things that are in the nucleus. I've got these things that have a positive charge, and I've got these things that have a neutral charge. I'm just putting an O for a neutral charge. So in there, I've got protons, okay, which are going to be positive, and they're found in the nucleus. And I've got neutrons, which are going to have no charge, and they're going to be found in the nucleus. And then finally, I've got one last thing. I've got these little negative guys on the outside, all right? And these are our electrons. And they're going to be negatively charged, and they're found in the, basically it's on the outside or the orbital or the cloud. In the cloud. Okay, so that's going to be our biggest thing that we're going over for atoms. We're not touching too much into this for biochem and everything. It's just basically the structure of an atom, so that you've got protons in the middle, you've got neutrons in the middle, you've got electrons on the outside. And it's because of that right there that is going to lead into carbon and why carbon behaves the way that it does. But you've got to make sure you understand the whole outside electrons are on the outside, and we want a certain number of electrons there. Anything on that? Case, got any questions on chemistry? All right, good. Glad. All right, now we get into, we'll make this, we're going for the aesthetics, water. All right, we're going blue for water. And so within water, if I were to look at it, remember it's composed of a big oxygen and two little hydrogens. Okay, so I've got a big oxygen and two little hydrogens. And remember on this thing, so oxygen has 6 valence electrons. They want 2 more to get to 8. So it's going to share them with those hydrogens. Because it's sharing it, it's going to have a specific type of bond. All right, so within this single water molecule, this bond between these hydrogens and this oxygen right here is going to be a polar covalent bond. That means it's going to share those electrons. And so that's how they're going to fill their outer valence, so that way they're happy, everything's peachy keen, everyone's just big chilling. But it doesn't share them evenly. That's why it has that term polar on there. So it means one of them's going to hog it a little bit more than the other one, and it's the one that's more electronegative, meaning it wants those electrons more, and that's going to be the oxygen. So that oxygen, it's going to have those electrons more, so it's going to be slightly negative. The hydrogens are going to be slightly positive. So it creates this polarity on there. Okay. And water likes to bond to other water, though. All right. So it forms this little bond. Let's say, and we go to oxygen, hydrogen, hydrogen. So now I've got water bonded to other water here, but this is no longer a polar covalent bond. What this kind of bond is right here, it's a hydrogen bond. Okay. If we ever boil water, if we ever freeze water, if we ever do anything with it, we're not dealing with breaking apart the actual single water molecule. So I don't separate hydrogen and oxygen, otherwise things might get a little explosive. What I actually do is I break that hydrogen bond between them. So if I've got ice forming, I've got a ton of these hydrogen bonds between water molecules. If I've got water, I've got less. If I've got gas or steam, I've got even less hydrogen bonds. So as I get more and more energy, the more energy I have, the more of those hydrogen bonds I break. And that's how I get between my different transitions between my states of solid, liquid, and gas. Okay, so now we got to talk about our properties. How y'all doing today? Great. Great, glad you're here. All right. Properties. So this is our first, or when you had one of your free responses, we talked about the properties of water. So property number one of the biggest ones is going to be cohesion. Okay. And in cohesion, we've got water to water. So water bound to other water. And you don't have to write it exactly like I do. You can write water to water. You can do whatever makes your little heart happy. Okay. So water is bound to other water. Because remember we said water is polar, so it likes other polar things, especially water. So it's going to form a little bond between that. Because of this right here, and this bond, remember we said between water and water, right here, it's called a hydrogen bond. Wake up. All right. Because of this right here, it leads to a phenomenon called surface tension. This is a big thing that people missed on their free response with water, because what they did is they put one of the properties is cohesion, another property is surface tension. It's the same thing. Surface tension is because of cohesion. So surface tension is water holding those bonds, and as long as that hydrogen bond is stronger than the force of gravity on that object, things can float on water. That's how we can have a water strider that walks across the top of the water. That's why if you're really, really, really careful, you can balance a paper clip on top of water. That's why water, you can have that bubble or that penny with all that water that stays on top of it, forms that drop that hangs over the side. All right, and it's because of surface tension, because of cohesion, water bound to other water.
So can we use cohesion and water, and surface tension interchangeably?
I wouldn't. The biggest thing you need to know is the concept of cohesion. You need to understand that surface tension happens because of cohesion. That's actually a good question. Okay, so number 2. All right, we can have cohesion where we have water bound to other water, but then water can also bind to what?
Polar opposites.
Okay, other substances. So, and they have to be. The thing about them. That sounded painful.
No, it actually didn't.
Oh.
I'm
Okay.
surprised.
Adhesion. All right, and what adhesion is going to be? It's water to other polar surface or other polar things. And it forms a hydrogen bond there too. Okay, so we've got water to other polar things. That's adhesion right there. That's why water can stick to glass. That's why water sticks to your shirt. That's why water sticks to your windshield. Unless you put Rain-X on there, because then you've essentially made your windshield non-polar. Or you can put cooking oil, like someone said, if you want to fall on a budget. Yeah. Okay. Number 3. So that's 2 of our big ones. Number 3 is going to be, it's got high specific heat. Okay. So with high specific heat, it's going to require tons of energy to change temp. So it's going to require a bunch of energy for water to change temperature. That's why it seems like it takes forever for water to boil. It's also why you can have water that gets really warm, all right, because it requires a ton of energy for it to have high specific heat, or to change its temperature. It's also why water's really also good at moderating temperature in coastal areas because of that high specific heat. Okay, so that's our next one. Is water requires a lot of energy for it to change its temperature. Number 4. Something to do with boiling, basically. It's got a high heat of vaporization. Sorry, my writing is basura. Thanks. All right. High heat of vaporization, meaning it requires a lot of energy for it to change state. So for water to become vapor, it means it has to go from liquid to a gas. It requires a lot of energy to do that. So temperature-wise, it usually happens at 100 degrees Celsius. All right. So that's usually average amount that it needs for it to boil. Obviously, some can happen a little bit lower. That's why you can have a puddle of water on the ground, and that whole thing evaporates off, even though it never hits 212 degrees outside. All right, but it still requires a very high amount of energy for that water to go from a liquid to a gas. And so, because of this, it leads to evaporative cooling. And evaporative cooling is a really fancy, high-tech name for sweating. So sweating to cool off. Because we start sweating, and what happens is that liquid that's on our surface of our skin is going to evaporate, and when it does that, it removes a tiny bit of kinetic energy. That kinetic energy is what's raising that temperature. All right, so it removes a tiny bit of that kinetic energy, and it's going to cool us off. So that's why we sweat and sweat and sweat to cool off when it's higher or hotter and hotter. We've got two more properties that we've got to talk about. All right, property number 5 is going to be a good solvent. But can water just dissolve anything? No, it can only dissolve specific things. It's good at dissolving polar substances. So for instance, if I were to put sugar in water, it's going to dissolve. If I were to put salt in water, it's going to dissolve. They're polar. If I put oil in water, no matter how hard I try, no matter how hard I shake it, I can shake it like a Polaroid picture, and it's never going to dissolve, right? Because that's not polar, but it'll dissolve polar substances. And then finally, we get our last one, and my favorite of all of them. Ice is less dense. So ice is less dense than water. Okay. So ice is less dense than water, and so ice floats. Okay. Good morning.
Is that yours?
Is what mine?
Ram.
Yeah.
Just get it?
Yeah, I got it this weekend.
It is here. You're gonna have to check it out.
Okay.
You got it?
Okay. So ice floats, and because of this, we can maintain life in aquatic environments. That stupid truck gets better gas mileage than my Jeep did somehow. Well, especially that. Even it got better. It gets better gas mileage than almost any SUV I looked at this weekend.
Is it lifted or no?
No, it's big though. It's a diesel. I
crazy.
averaged 29.9 miles to the gallon on the way here.
I was gonna say, where's your car?
Rip.
Oh, transmission fee?
Okay. That's unit 1. Let me make sure.
Catch Winnie.
Oh wait, I forgot biomolecules.
Okay,
I was like, how is that so quick on unit 1? We forgot biomolecules. Let's say each unit should take about.
Is that the macromolecule?
Yeah, that's macromolecule. Half hour. Thank you. Any questions on water?
We're gonna do
Yes, Grace?
the interfusion and the bonds between water and polar things is a hydrogen bond cell.
Yes. Yeah. Yeah. There's a lot of bonding that's going to take place with water. Is going to be hydrogen bonding. That's a big thing. So the biggest things for hydrogen bond: water to other polar substances, water to water, and the other big place where we see hydrogen bonding is going to be on how we get our secondary structure on proteins. So you know how we get the alpha helix and beta pleated sheets? All right, we'll get there. You just hold on.
You don't know.
I'm gonna have a busy night tonight.
I never heard those terms in my whole day.
What's a protein? Okay. Biomolecules. I'll make sure I spell it right. Biomolecules. All right, so that was page 1. Page 2. I'll just type. No, I won't. Okay. So all these biomolecules are called organic. And they're called organic not because they're like hippie molecules that like you get half the amount and pay twice the price and everything for. It's because organic in scientific terms means based off carbon. All right, and so carbon has 4 valence electrons. Oh, you got permission to leave? Okay, so it has 4 valence electrons, meaning it can bond with up to 4 things. Okay. And so there's 2 big terms that we've got to talk about for biomolecules. All right. Big term number 1 is going to be dehydration synthesis. I'm just going to type these because I realize my handwriting is trash. Okay. So for dehydration synthesis, it's also known as a condensation reaction. Okay, so a condensation reaction. Because you might hear it in different terms. Sometimes some textbooks use condensation, sometimes they use dehydration synthesis. And so when I'm doing this, I'm linking monomers to make polymers. All right, so I'm linking monomers to make polymers. Remember, synthesis means to make. I'm making something larger. And when doing this, a water is released. I put release because for some reason a lot of people heard dehydration synthesis and they confused it thinking that water had to go in it. But remember, water is released. When you're dehydrated, that means you lost too much water. So are you still like half asleep? All right. And then we've got the opposite of dehydration synthesis. So if I don't want to build stuff, that means I want to break it down. Hydrolysis. And when I'm undergoing hydrolysis, I'm going to break down polymers. Break down polymers into monomers. And water is used. So water must come into this. Hydrogen's going to go to one part, half of it. The OH is going to go to the other half. The hydroxyl is going to go to the other half. Okay. Any questions on these 2 concepts before I go into the big 4? All right. Yes. Sorry. What? Yep. Gryffindor, Slytherin. I don't know the other 2. Yeah. I've watched the first. How many movies are there? 8. I've watched the first 7 as background noise, but I've never actually sat and paid attention to them, even though my sister has them like all memorized. Yeah. All right. First one we're going to start out with carbohydrates. Carbohydratos. All right. So it is the polymer. So the polymer is going to be carbohydrates. All right. The polymer is going to be carbohydrates. And the biggest reason that these are going to be used for is going to be energy and structure. That's their big uses. So the monomer of a carbohydrate is going to be what's called a monosaccharide. Monosaccharide. The most common one is glucose. Okay, the most common one is glucose. And its use, fuel or energy. I'll put energy. So that way you're not like, it's like a car. So the monomer is monosaccharide, its use is energy. All right. If you see pictures of them, so sometimes you might get a picture of something and it might say like, identify what this is. Usually a monosaccharide has an oxygen and then it's either in a hexagonal shape or a pentagonal shape. So it's going to look something like this. You might see other stuff coming off it, but if you look at that general basic structure, this is what they look like. Okay, so that's what a monosaccharide is going to look like glucose. Okay, the polymer, we've got a few big polymers that we're going to talk about. The most common polymers that we have are going to be cellulose, and I'm going to go through each of these. So cellulose is in plants, not plants. Yeah, and so that's going to be for structure. The cellulose makes up the cell wall. So plants have to have structure. Their cell wall gives it structure, and that's what cellulose does. We eat cellulose all the time. Some of us try and have more than others. Any clue what cellulose is? It's on every one of your nutrition labels.
Oh my god, I do see that.
It's fiber. Cellulose is fiber. We cannot digest it. That's why it's like your bumhole's toothbrush, because it helps stuff go through. We get full from it, but we don't really digest it. And a lot of people with, let's say you're backed up, which some people are, and that's why I say good luck. What do you tend to eat? Fiber, because we can't digest it. It flows through you. Because it has a lot of fiber. That's exactly why you eat prunes. It has a lot of fiber. That's also why you eat like a Fiber One bar. So we've got cellulose. We also can have starch, which is also going to be in plants. Okay? And so that starch is in plant. Ooh. Okay? So the starch, though, I'm just going to write this. This is stupid. Is going to be for energy. Plants need energy too, so they store starch. What do you generally associate with foods that are high in starch?
Potatoes.
Papas. Yep, your potatoes. Okay. Potatoes are very high in starch. Potatoes are grown in the ground. It's not like a plant is growing these potatoes like, here, human, I shall sacrifice myself to the gods. Have my potatoes. All right. The reason that a plant has potatoes is that way when it doesn't have a lot of energy, it can break down that potato for energy. All right, because it's just a giant like storage mechanism or a reserve. All right, then we can also have glycogen. And that's going to be in animals. All right, and glycogen's energy for us. That's carbohydrate storage. If we get short on energy, we break down glycogen. And then finally, chitin. I don't know why I put a capital H. C-H. I'm going to rewrite that. Chitin. C-H-I-T-I-N. It's not chitin. Justin, he made me a shirt. It says, "Are you kiting me?" Because it looks like it says, "Are you chitting me?" Okay. So chitin is going to be in animals. Okay. And it's used for structure. Oh, it's not only in animals, it's also in fungi. This is what the exoskeleton of a bug is made of. This is also what a mushroom is made of. It's chitin. It's a type of carbohydrate. It's these really, really, really long chains of carbohydrates linked together.
What the heck is... She's a little...
What the?
She's crazy. Freaking crazy.
Oh, rip.
Hey, is that a virus?
Please hold momentarily, people. On the
Doors right
computer.
there.
It's wide open.
She's quaking. Alright guys, that's the end of the lesson.
I think it's just Google Cast is tweaking. Alright, we're going to recast this. Sorry, people on the computer. For those of you who can't see, the projector just totally spazzed out, and so that's why we're taking a momentary break.
Technical difficulties.
Yes, please hold for technical difficulties.
What do you mean? Doesn't work.
Oh yeah, connection failed. That was tweakerish, man. Happy Monday. There we go. All is now well on the Western Front. All right. So that was carbohydrates. Now we got to go into carbohydrates is one of the longest ones. Lipids. All right, also known as fats. Yo tengo mucho. Biggest thing to know about lipids, they're not a polymer. Yes, I'm yelling this. That's why it's all in caps. Lipids are not a polymer. They're not made of a monomer. Remember, we've got carbohydrates, we've got proteins, and we've got nucleic acids. All of those are polymers. They're all made of a building block. Lipids are not made of a repeating subunit. They're not made of a polymer. One of the three does. I'm about to draw them out. So there's three big types. Type number 1, triglyceride. This is what I have a lot of. Okay, so triglycerides are going to look like this. They're going to have a glycerol right here, and they're going to have these really long tails. Okay, I just draw it like this to make it faster, but if you actually look at it, it's like carbon, 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 all right? But when you're drawing it in like organic chemistry, when you take that in college and everything, every corner, when you're drawing biomolecules, so if you go like this, every one of these actually represents a C. So a triglyceride is a glycerol with 3 real long hydrocarbon tails. Okay, so I just wanted you to see what both of them look like. Its main use, energy. That's why we store fat. It's energy for if we need it later on. So if I have excess calories, all right, or if I have excess food that I'm taking in, my body thinks, oh, I'm going to save this. I don't want to just waste it. I'm going to save it for later on. So that's what a triglyceride does, okay? That's why if your body, let's say, what's the biggest way to lose weight? What do you have to say you have to do? Well, you got to eat healthy, but what else is a big one? Work out, exercise, because when you exercise, you lose a lot of energy. If you're not eating the right amount of energy every day, your body's going to go to its storage. Its storage of energy is fat or triglycerides. That's why you start burning fat, because your body needs that energy. Yep. All right. Phospholipids. Yep. Yo ho, the fat life for me. Yes, if you were to take 2 people, put them on like a deserted island, the fat one would live longer.
That's the life one.
I shall live forever.
Not only will you not get kidnapped, but you also survive.
Okay. Phospholipids look like this. They've got a phosphate head, all right, and this thing is going to be polar. But then they've got, remember, these hydrocarbon tails. So like I said, I'm just drawing it both ways so you can see. Normally I'll just draw it like just the angles. Okay, so they've got these big, long phosphate head and these long hydrocarbon tails. Phospholipids are going to be found in cell membranes. Okay, phospholipids are found in cell membranes. Okay. Then I go to my last one, steroids. If I don't get through immune system today, this morning, I'm going to go through it in class because I have a flow chart that shows everything. Yeah, I'll go through this in class if I don't get through it here. Phospholipid is not used for energy. Phospholipid is going to be more for structure because it's going to be used. It's what all cells have a cell membrane on the outside, and some organelle have cell membranes, and so it's all made of a phospholipid, like bilayer. All right, steroids. They're going to look funky. They're going to be. So a steroid looks like this. So it's not a single hexagonal shape. All right, it's got this ring structure. And a big one's going to be used for cholesterol. Good morning. Thank you. Was that paperwork for PO2?
No, that's extra safety.
Oh, perfect. Right on. Thanks, man. So cholesterol and communication. So we associate cholesterol with being bad for us, but cholesterol, we're going to learn a lot of it in Unit 3. Biggest thing about cholesterol, it maintains membrane fluidity, which is just like that, doesn't help whatsoever. Our membranes have to be fluid-like, meaning they have to be able to move around. If it gets really cold, they'd get really rigid, and our cells could basically rupture or break. All right, it's kind of like being if I took a little. Have you seen a bubble when it freezes? Like a soap bubble?
Oh yeah.
Okay, so if I took a soap bubble, you know how they can kind of move around and they're malleable and they can flex and all that stuff. If I froze one, if I were to touch it whatsoever, the whole thing will pop because it doesn't have that fluid-like movement anymore. Cholesterol does that to our cell membranes. So it makes our cell membranes flexible. It helps them be able to move around and everything, which helps aid to us. We have to have it. Okay. Really high amounts, though, can separate our phospholipids. So we don't have phospholipids right next to each other. They have a little bit of a gap because of cholesterol. If I have too much of it, then it can be bad.
Oh, in between this? Between the carbo?
Yep. So between phospholipids, so it's like phospholipid, cholesterol, phospholipid.
Yeah.
Yep. So it's like this one right here. That's phospholipid. We'll spend a lot of time when we're going over membrane structure next unit. Okay. So we've got lipids, and then now we're on proteins. Yeah, I'll probably do the immune system flow chart in class because I don't want to rush through it all. Biggest thing for a protein, its monomer is an amino acid. All right, and that amino acid is going to look like this. It's going to have this to this. Okay, so we've got an amino group, and we've got a carboxyl group. And then we've got our functional group, basically. So that's what makes the amino acid behave different is that R group right there, that functional group. All right, all of them are going to have this same basic building block. Remember when you did your foldable in your thing? In the middle, you had that amino acid. You had two amino acids linked together. It was two of these linked together. All right, and so that's the building block of these proteins. And in a protein, there's going to be a couple different uses we have proteins for. So it might be, so I'm just going to put uses. It might be used for enzymes, which, just for general terms, speed up reactions. It might be used for storage. It might be used for transport. And it might be used for receptors. For instance, the receptors on the outside of like a helper T cell. Okay, so proteins. So these are some of the big uses that you need to know for now. And so on our structures for this, as I'm doing this, if you have any questions, please don't hesitate to ask. Because if you have questions, I guarantee other people have questions. Yes.
Are we going to need to know this?
You should be able to recognize. So all of these things, you see how I'm drawing the general layout of stuff? Yes. You should be able to recognize it. So if I were to give you a picture, let's say I gave you like this picture right here. And I'd say, using figure 2-1 or 2.1, which type of biomolecule is seen below? And so you say, oh, okay, well, that's a phospholipid, meaning it's a type of lipid. Or if you were to see like this right here, wherever that amino acid went, you should be able to look at that and go, oh, okay, well, there's that. Okay. Or if I showed two of these linking together and kicking off of water and asked which process is taking place, you should be able to say, oh, it's dehydration synthesis. Or if you saw water going into it, you say, oh, that's hydrolysis. Okay, so structures, I've got primary. And primary is just going to be the linear order of amino acids.
And then the polymer is polypeptide.
Yeah. So the polymer, I'm just going to put AA so I don't type out amino acids. The polymer is a polypeptide, otherwise known as a protein. amino acids. So it's just the fact that what order do you go in? That's your linear or your primary structure, not primary. Yeah, it's your primer structure. This is your foundational structure. Yeah. Make sure you like and subscribe. Secondary. All right, and there's two big things for secondary structure. We can have alpha helix or beta pleated. All right, alpha helix is going to look like beta pleated goes. Okay, and all of this happens because of hydrogen bonding. Okay, hydrogen bonding. So we've got hydrogen bonds that's going to happen between the amino group of one and the carboxyl, or in the the carboxyl group of another one. Then I can go into tertiary. Okay, which can be unique 3D structure. Did I spell unique right?
Yeah.
Okay. So unique 3D structure, and it's due to R group interaction. Meaning, now I have, so all those R groups, some are going to like each other, some are hydrophobic, some are hydrophilic, some are basic, some are acidic. So all of these things behave differently. And so now this is going to cause it to fold in its own unique 3D shape. And then finally, quaternary. Okay, and that's going to be one or more tertiary polypeptides. Cool. We're almost done with biomolecules. We got one more. Makla and Shania, aren't you glad you don't have to come to these anymore?
Okay, I have a question. Where's German? What is she freaking out about?
I know, that's what I was thinking.
Where is German?
I wasn't even thinking.
She's like, no, cool, you
I don't know.
because I need an extra hour.
That's 30 minutes tonight.
Okay, so then we got nucleic acids. I told people unless they had questions, you can watch it at home.
Yeah.
I don't have time at home.
I know some people though do better at home. They don't work well in the morning, and so some people I told them I go, if you don't have questions, there's no point in you coming, unless you like to be here and hear it firsthand. So nucleic acids is what? This is the last one for Unit 1 for as far as biomolecules. Its monomer, okay, is a nucleotide. And a nucleotide, I'm going to draw it, is going to have a phosphate. It's going to have a sugar, a pentose sugar, and it's going to have a nitrogenous base. So I'm going to put NB. So phosphate, sugar, nitrogenous base. Phosphate, sugar. Hey. Base. Okay, phosphate, sugar, nitrogenous base. These are the building blocks of DNA because that's what nucleic acids are. They're either DNA or RNA. Hi, Franco. Good morning. So we've got DNA, and we're going to write how these things are different. This has a deoxyribose sugar. So it's got a deoxyribose sugar. It's generally double-stranded. And it's going to have A, it's going to have C, it's going to have T, and it's going to have G. So it's got those 4 nitrogenous bases. And then I can have RNA. And it's going to have a ribose sugar. Generally single-stranded. And it's going to have A, C, U, and G. Adenine, cytosine, thymine, guanine.
What is it, you?
Uracil. Yeah, it's uracil. Okay. Gattaca? Dope sauce. I wish that was on Netflix. Gattaca.
You watched the freshman year.
It was a great movie. All right. So now let's go to Unit 2. I know. Okay, Unit 2. I'm going to start off with a big thing of just cell theory. The most basic form of this, the basis of all of this right here is all things are made of cells. All living things are made of cells. Cells equal the most basic unit of life. And cells come from other cells. So all living things are made of cells. Cells equal the most basic unit of life, and cells come from other cells. You have a bottle? I'm proud of you. I can't keep calm. I'm a cat. Oh my God, Grace. Of course you are. All right, so let's talk about the origin of life. So origin of life. There's 2 big hypotheses. So number 1 is going to be organic soup. It's all natural. So organic soup could have a day. I get you. So organic soup model is saying that in the aquatic environment, because there was water back then, we had the basic molecules. Yep. Basic molecules like methane, ammonia, hydrogen, and CO2. So we had these basic molecules, and they can be reformed to make biomolecules under the right condition. For the record, let it know that slurping came from Mark. Okay.
We haven't had an ASMR segment, which is getting mad. Oh, I got a perfect sound.
So the basic molecules, CH4, NH3, H2O, CO2, so they can be used to make biomolecules. So the building blocks of life that we need. That's the organic soup model. We also have what's called the panspermia. All right, basically meaning big ball of fire. So this big ball of fire, a meteor, not media, all came from the mainstream media. A meteor brought them biomolecules. Okay, so it brought these biomolecules like their amino acids, and so we have evidence because we have there's one meteor that has a lot more amino acids than we even have in life, right? And so the order that this stuff occurred in, so how life got started, we have the order of events. Okay, what do you think came first, the monomer or the polymer? The monomer. So order number one, organic monomer. So that organic monomer was probably brought here. Order number two, those monomers started to form together and form polymers. Okay. Number three, eventually, when lipids are in water, they start to form a ball automatically.
It's a fat membrane.
Okay. A protobiont.
Oh.
Okay.
And the next one is like lipo something.
Liposomes, yeah.
Wow.
Okay, so big events. Organic monomer was formed, organic polymers were formed, protobionts were formed, and then eventually we got DNA organisms. That's the big four steps on how it's believed that life came on Earth.
You have to say ASMR and they're gonna be like, what?
Yeah, you can't just get
No,
them out
that's
of
just,
nowhere.
those are the dumbest videos ever.
But like, what if they're like listening to headphones? You didn't even give them a warning.
Okay. The most basic cell type is what kind of a cell? Starts with a P, into the prokaryote.
Prokaryote.
Okay, prokaryotes. So we're going to go over prokaryotes first, all right? But, so we've got to say all cells, regardless of their type, have these four things. So they all have genetic material. They all have a cell membrane. They all have cytoplasm. And they all have ribosomes. You see those 4 books in the second shelf, there's a whole case of them.
This week on Wednesday or Thursday if you're available. I'm doing maths with them.
Okay, so all cells, regardless of their type, have genetic material, cell membrane, cytoplasm, and ribosomes. And so now we're going to go to the most basic one of all of them. The Miguel. Okay. The prokaryote. So does a prokaryote have genetic material?
Yes.
Heck yes, it does. Does it have cell membrane? Heck yes, it does. Does it have cytoplasm? Heck yes, it does. But does it have ribosomes?
Yes,
No,
it does.
because there's not a nucleus. Wait, am I dumb?
It does, of course.
How
How
was
was
it?
it?
Wait.
They're majestic.
All cells. LOL, that's what I said. Wait, which one is that?
All cells, regardless of their type, have those 4 things. All right. So it's one of the big things that we're going to write about here is, so prokaryotes they have no nucleus or membrane-bound organelle.
Organelles that have like.
So organelles that have a membrane on the outside, they have a phospholipid bilayer. That's the big thing is, so prokaryotes do not have membrane-bound organelles, so they don't have a chloroplast, they don't have a mitochondria, they don't have the endoplasmic reticulum, but they have ribosomes because a ribosome is not membrane-bound. Okay. They tend to be very, very small. And they have a cell wall generally. If bacteria, so some bacteria have, I'm not even going to put that. Okay. So prokaryotes, no nucleus, membrane bound organelle, and small. Which leads us into one of my favorites. Okay, endosymbiotic theory. Step 1, big prokaryote. Eight, little prokaryote. They started working together. Okay, and so they started working together. So I had a big prokaryote taking a little prokaryote. They started working together, and this led to. How do I spell lead? Is there an A in there? LED or LEAD?
Wait, like led to?
It led to. Would it be LED? Okay. Light emitting diode. To evolution of eukaryote. That's how eukaryotes came along. Eukaryotes have a nucleus. Eukaryotes have membrane-bound organelle. The reason why is because it started eating stuff that wasn't once inside of it. And so now I've got these little structures in there that are going to do little jobs for it. All right. Thus the endosymbiotic theory. These little structures came into the cell and started doing jobs for it. They're working together, and now I have organelle. Okay. So the evidence for this. Okay. Our evidence for endosymbiotic theory is going to be the membrane. Good morning. So membrane structure. Evidence is going to be own genetic material. And evidence can be replicate on their own. You know the two biggest organelles that are said that we collect all this evidence from for the endosymbiotic theory? So evidence for the mitochondria. I should have written this earlier. Mitochondria and chloroplast. Yeah, we're almost done. All right, organelles. Do you guys need me to go over those or anything? I feel like I was literally just gonna list them all out. Viruses. Okay, they have a capsid. So no cell membrane. And capsid's protein. Sorry, I should have written that after.
No cell, what do you mean? Oh, no cell membrane.
They have no cell membrane. They do have genetic material. And they don't have cytoplasm. Or ribosomes. Okay. So they have no cell membrane, protein, they have genetic material, they have no cytoplasm or ribosomes, and the life cycle. There's lysogenic. And in lysogenic integrates integrates into host DNA and replicates. Lytic Assembles and breaks out. And we're gonna stop there because it's 7:30, and I need you guys to have time for breakfast. If you want to go grab it real quick.
I don't need breakfast.
Okay. So we're gonna stop there. I'm gonna go over the flow chart of the immune system in class. It won't take too long. I'm just gonna outline it. But I need you guys to have a chance for breakfast. We don't need starving children. Siriana,